Welcome to MarkScheme. Kinematics. Everything you need made visual. You kick a ball into the air. It rises, it curves over, it comes back down. Here's the question that opens all of mechanics. Before it even lands, could you predict exactly where it hits the ground? And how fast? And when? The astonishing answer is yes, with nothing more than the starting speed, the angle, and the pull of gravity. Kinematics is the mathematics of motion, position, velocity, and acceleration, the graphs that link them, and 4 equations that turn a kickball into a solved problem. This is the foundation the whole course stands on. Here's exactly what we cover, straight from the syllabus. Physics, topic A.1. Position, velocity, and acceleration, and the difference between distance and displacement. Average versus instantaneous. The motion graphs and the 2 rules that run them. The 4 equations of constant acceleration. And projectiles, right up to the effect of air resistance and terminal speed. And here's the good news for everyone watching. Every single part of A.1 is SL/HL Common Core. There is no higher level only content in this topic at all. So whether you sit standard or higher level, all of this is on your paper. No prior physics is assumed either. We'll build vectors and components from scratch as we go. 2 words that look the same and are not. Distance and displacement. Walk 4 meters east, then 3 meters north. The distance you traveled is the length of your path. 4 plus 3, 7 meters. That's a scalar. Just a size. But your displacement is different. It's the straight arrow from start to finish. 5 meters northeast. It carries a direction. That's a vector. Distance and speed are scalars, sizes only. Displacement, velocity, and acceleration are vectors. They have a direction. And in physics, that direction earns you or costs you marks. Hold that distinction. It runs through everything that follows. Now speed things up, literally. Velocity is the rate at which position changes. On a displacement time graph, that rate is the gradient. Take 2 points a while apart. The gradient of the straight line joining them, change in displacement over change in time, is the average velocity over that interval. But the ball doesn't move at one steady rate. It's speeding up. So what's its velocity at a single instant? Shrink that interval until the 2 points collide, and the chord becomes a tangent. The gradient of the tangent at one point is the instantaneous velocity. And accelerations is the very same idea, one level up. The rate of change of velocity. The gradient of a velocity time graph. Position, velocity, acceleration. Each is the slope of the one before. These 3 graphs are the language of motion, and they're all connected. Displacement time, velocity time, acceleration time. Reading left to right, each graph is the gradient of the one before. The slope of the displacement graph gives the velocity graph. The slope of the velocity graph gives the acceleration graph. Here the velocity climbs at a steady rate, so the acceleration is constant, a flat line. But the velocity time graph hides a second treasure. The area underneath it, between the line and the time axis, is the displacement. Rate of change lives in the gradient. The total change accumulates as area. Remember those 2 rules, and half of kinematics is done. Let's earn the equations rather than just quote them. Take an object under constant acceleration. Its velocity time graph is a straight line. From a starting velocity up to a final velocity v over time t. Everything falls out of this one trapezium. First, the area under the line is the displacement, and it's a trapezium. So displacement equals a half times u plus v times t. That's equation 1. Second, the gradient is the acceleration. V minus u over t. Rearrange, and v equals u plus at. That's equation 2. Now combine them. Substitute v's equals u plus at into the first equation, and the algebratides to s equals ut plus a half a t squared. Equation 3. And if you eliminate the time between them instead, you get v squared equals u squared plus 2as. Equation 4. The one with no time in it. 4 equations, 1 graph. And here's the exam gift. All 4 sit in your data booklet. You never memorize them. Your only job is to pick the right one. Here's the idea the whole topic is built on, and it's beautiful to watch. A projectile's velocity is a single vector, but we split it into 2 pieces that don't talk to each other. A horizontal part in gold and a vertical part in purple. Watch what each one does as the ball flies. Gravity pulls straight down, so it only touches the vertical component. The horizontal gold arrow never changes length. With no air resistance, nothing pushes sideways. So horizontal velocity is constant. The vertical purple arrow tells the whole story. It shrinks on the way up, hits 0 at the very top, then grows downward as the ball falls. One steady motion across, one accelerating motion up and down, glued together into that curving blue velocity arrow. And look at the graph on the right. Because the horizontal velocity is a flat constant line, the area growing underneath it is the horizontal displacement, and it swept out exactly as far as the ball traveled across. Area under a velocity graph is displacement, live, in front of you. Resolve into components, treat each direction on its own, and a curved flight becomes 2 straight-line suvat problems. Let's build a ladder of examples, easy to hard, all my own numbers. Number 1, 1 dimension. A car brakes from 20 meters per second at 4 meters per second squared. Find how long it takes to stop and how far it travels while stopping. First, list what you know. Initial velocity u is 20. Final velocity v is 0. It stops. And the acceleration is minus 4. Negative because braking opposes the motion. Getting that sign right is half the battle. For the time, pick the equation with u, v, a, and t. v equals u plus at. 0 equals 20 minus 4t. So t is 5 seconds. For the distance, the neatest choice is s equals a half, u plus v, times t. A half times 20 times 5, 50 meters. Stops in 5 seconds over 50 meters. Number 2, vertical motion. And the first place, signs really bite. A ball is thrown straight up at 15 meters per second. Using g equals 9.8. Find how high it goes and how long it's in the air. Set a convention and never break it. Up is positive. Then the launch velocity is plus 15. And gravity, pulling down, is minus 9.8. At the highest point, the ball is momentarily still, so v is 0. Use the no time equation. V squared equals u squared plus 2as. 0 equals 15 squared minus 19.6s, giving 11.5 meters. For the total flight time, the ball comes back to your hand, moving downward at 15. So v is minus 15. Then v equals u plus a t gives minus 15 equals 15 minus 9.83. So t is 30 over 9.8, about 3.1 seconds. Notice the symmetry. The trip up and the trip down take equal times. Number 3. The full projectile. And this is where resolving pays off. A ball is launched at 25 meters per second, 30 degrees above the horizontal. Find the time of flight, the range, and the greatest height. Step 1. Always. Resolve the launch velocity into components. Horizontally, 25 goes 30 is about 21.7 meters per second, and that stays constant the whole flight. Vertically, 25 is in, 30 is 12.5. Now you have two independent one-dimensional problems, linked only by the time. The time of flight is set by the vertical motion alone. Up and down are symmetric, so the total time is twice the launch. Vertical velocity over g, 25 over 9.8, about 2.55 seconds. The range is then pure horizontal, constant 21.7 times that time, roughly 55 meters. And the maximum height uses the vertical component only, 12.5 squared over 19.6, about 8 meters. 3 answers, all from splitting one vector in two. Number 4 is graph-based, and it rewards the two rules we built. A body speeds up for 4 seconds, then cruises at a steady 12 meters per second for another 6. From the graph, find the acceleration in the first stage and the total displacement. Acceleration is the gradient. In stage 1, the velocity climbs from 0 to 12 over 4 seconds. So the acceleration is 12 over 4, 3 meters per second squared. In stage 2, the line is flat, so the acceleration there is 0. Displacement is the area underneath. Split it into a triangle and a rectangle. The triangle is a half times 4 times 12, 24 meters. The rectangle is 6 times 12, 72. Add them, 96 meters in total. No equations memorized, just gradient for the rate, area for the distance. In reality, air pushes back. Fluid resistance or drag always opposes motion and grows with speed. On your paper, this is qualitative only, and it is still Common Core. But you must know its effects. For a projectile, drag steals energy. The range shrinks. The peak is lower. And the path is no longer a clean symmetric parabola. It comes down steeper than it went up. Now drop an object and let it fall. At first, it accelerates, so drag is small. But as it speeds up, the drag grows, until the upward drag exactly balances the downward weight. Then the net force is 0. The acceleration is 0, and the speed stops rising. It has reached its terminal speed, a steady maximum, shown by the curve leveling off. That's why a skydiver or a raindrop falls at a constant top speed. Now the exam craft that turns understanding into marks. 1. Choose a positive direction and commit to it. If up is positive, gravity is minus 9.8, and anything moving the other way carries a minus. 2. Use g equals 9.8 every time. And before you touch a formula, list your 5 quantities, u, v, a, s, and et, so you can see which one to reach for. 3. The big projectile rule. Resolve into horizontal and vertical components first. They run independently and only share the clock. And 4. The suvat equations are printed in your data booklet, so don't waste effort memorizing them. The skill is picking the right one, then quoting your answer to about 3 significant figures with units. Finally, the 4 traps that quietly cost marks. 1. Treating distance and displacement as the same thing. One is the scalar length of the path. The other is the vector from start to finish. 2. The classic projectile slip. Plugging the launch speed of 25 straight into suvat instead of resolving it. Always use the component. 3. Writing acceleration as plus 9.8 when you've called up positive. Gravity points down, so it's minus. And 4. The most dangerous. Using the suvat equations when the acceleration isn't constant. The moment drag enters, they no longer apply. Dodge these 4 and Kinematics hands you easy marks. And that's A.1. Kinematics, fully covered. How we describe motion, the language of graphs, the 4 suvat equations, and where they come from. Projectiles as 2 independent motions, and the qualitative story of drag and terminal speed. Every bit of it is on both the standard and higher level papers. Next in the course, what actually changes motion? Forces, Newton's laws, and momentum. For more, that's MarkScheme.app. See you there.